All right, so today we're going to be talking about how um, pendulums follow not momentum, conservation of energy as well. Because similar to how the spring mass system works, not only does the the pendulum oscillate, but it also applies to you can also use conservation of energy. So conservation of energy says the total energy at any point has to equal the kinetic energy at that at one point plus the potential energy at that point. So um, this is always scalar, so that means it's always going to be positive. But the kinetic energy or the potential energy could be zero at any point depending on the position and the speed. But when I talked about conservation of energy with springs, we talked about elastic potential energy. The thing is, and let me just draw this out. So let's say we have a pendulum here, and it has um, some like angle, which is like right here. Or no, let's just say it's right here. So basically, we have to if we're trying to find the kinetic energy and potential energy at that point. Let's say like this is where the equilibrium position is. This is where x equals 0, and then at this point, like let's say at a later part, that's when x equals a. Or if you like using y instead of x because of it's vertical oscillations rather than horizontal oscillations, then go right ahead. So let's say we find let's say we were to identify you know the kinetic energy and potential energy at 1/2 a. So the kinetic energy would just be 1/2 mv squared, right? But the potential energy would just be mg times 1/2 a. And this comes from potential energy equals mass times gravity times height, or the gravitational potential energy. Now, since there is no spring, there's no elastic or anything that's holding it back and has a restoring force besides the force of gravity. Like, say if it's like we don't have a stretching force, something to stretch, like a spring or a bow, that counts as elastic potential energy. But since this is a string on a like and it's a pendulum, there is no elastic potential energy, but there is gravitational potential energy because the height is always changing. All right. So basically, what we have to say is the kinetic energy at a point plus the gravitational potential energy at a point is equal to the total energy. All right. But but if we were trying to find the max kinetic energy, well, that'll just be 1/2 mv max squared equals k v max. And then for the max potential energy, then it'll just be mg times a. and this is the max height. So in this case, A equals max height. All right. So say if we were trying to find like the max like the max velocity. So find Vmax, but um, you're basically given um, the amplitude and the mass. So at that point, it would be K E max equals P, the potential energy max. And then you could do 1/2 mv squared equals mga, multiply both sides by 2, you get mv squared, or Vmax, equals 2 mga. And then the masses are cancelable, and you just get Vmax equals the square root of 2ga, which is actually similar to the kinematics equation, which is v squared equals v naught squared plus 2g delta s. So assuming it starts from rest, you just get v equals the square root of 2g delta s. Yeah. So if we were to draw this on a diagram of where the energy is at the certain points, so here's our pendulum. So let's say right here, and then let's have a point where it's at its max height, and let's have a point where it's at you know where it's at its lowest point. So this is where y equals 0. Let's say y equals like 0.3 meters. It doesn't really matter. Or just say y equals y1, just to be more apt, just to like say this applies to anything, not just 0.3 meters. And then this y equals a, and then y would also equal a. So because y equals 0, the potential energy equals 0. And since the potential energy equals 0, the total energy has to equal the max kinetic energy. So Ke is at its max. So let's say right here at y1, so Pe would just equal 1/2. I mean, no, that's Ke. Sorry. That'll just be mgy1. And then for the kinetic energy, it would just be 1/2 mv squared at that point. And then when you sum these two together, so Pe plus Ke at that point, that has to equal the Ke max because of conservation of energy. The amount of energy it's given right here has to equal the sum of these two energies, because Ke max plus the potential energy, which is 0, is just Ke max, which is the total energy. And I'm going to say this is equal to total energy. Alright, so we're given that y is equal to a. That means it's at its max height. So the potential energy is at its max because it can't go farther than that. And because energy is conserved, that means the kinetic energy has to equal 0. And because the kinetic energy is equal to 0, assuming there's a mass to this ball, or whatever object you want to call it, that means the velocity has to equal 0. So at that point, it is instantaneously at rest. So the total energy at that point equals the potential energy max. And same thing here. So PE max, V equals 0, KE equals 0, and then TE equals PE max.